everyone. Welcome and thank you for joining us today. I am Angela Bliss, a co-leader of the CIS Community of Practice on IARPIC, along with Ignatius Rigger, Elaine Runk, Maddie Smith, and Ching Hua Ding. The goal of this meeting is to share information on sea ice thickness and freeboard observations, including their availability and use, and to share about some recent updates to available data products. We'll continue this discussion on the topic of sea ice thickness at future meetings in collaboration with the physical oceanography and modeling teams on IARPIC that will focus more on models and model development. But for today's meeting, our topic is sea ice freeboard and thickness measurements from satellite and buoy observations. So our first presentation today is from Don Perovich from the Thayer School of Engineering at Dartmouth College and Chris Polashenski from Dartmouth and the U.S. Army Cold Regions Research and Engineering Laboratory. Their presentation today is titled Ice Mass Balance Buoys of the Past, Present, and Future. So we'll start first with Chris.
Great, thanks. Let me get the screen share fired up here. Can you see that?
Looks good.
All right. Well, hello everyone. Thanks for logging in to hear about ice mass balance buoys. I'm Chris, and I'll be joined by Don Perovich. He'll tag team in for the second half of the talk here. Don started the ice mass balance buoy program with Jackie Richter-Mengy and Bruce Elder at Krell. Early versions were deployed during the Sheba Field campaign in 1997. I didn't actually join the program until 2007, but together we've put out a whole bunch of buoys. We've had direct funding support from NSF, NOAA, NASA, and we've had the collaboration from so many people and other entities that it's a trap to try to put all the logos on because you for sure forget one and then feel really bad about it. So I didn't even try to. But we wouldn't have the buoy program without it being a community effort where so many people have helped us get buoys out, helped us with feedback on the buoys. I mean, basically, if you're heading to the Arctic and we see that you're going somewhere we don't have a buoy, just watch your luggage really, really carefully because we will slip a buoy into it. The buoys, which we call the next best thing to being there. We actually really like to go to the Arctic ourselves, but at some point you got to go home and leave. You can't take all the measurements yourself. They're basically just an automated version of the old school thermodynamic ice mass balance measurement. By that mean they're measuring the same thing you could measure if you were there with a drill, drilling a hole through the ice and measuring how the top and bottom of it have either grown or melted over time. The buoys consist of a cylindrical hull that's deployed through the air, snow, ice to ocean interface. The buoys are about 4.9 meters long in the standard configuration anyway, and they're about 4 inches in diameter. They float upright. They will survive out into open water, but they tend to get crushed during freeze up, so they don't always survive the full complete melt out refreeze cycle. At their top, they've got a shielded air temperature and pressure and barometric pressure sensor. They also have a downward looking acoustic rangefinder for finding the surface. Along the side of the buoy at 2 centimeter spacing is a temperature string all the way down through that air, snow, ice, ocean interface. In the upper section of the buoy is the data logger that controls everything, and the GPS for position, and the iridium antenna and modem for telemetering the data back home. And then deeper down in the buoy hull are the batteries and a counterweight. And at the bottom is an upward-looking acoustic rangefinder for detecting and tracking the position of the ice bottom. Together, this group of sensors measures where the buoy is in space as it drifts through the ice, the barometric pressure, which is fed into real-time forecast models through the WMO GTS forecast system, and that temperature profile through that interface. From the acoustic rangefinders and the distance measurements that they make, we can infer the depth of the snow, the ice thickness, and the surface or bottom growth or ablation. So the key feature of the SIMB is its ability to discern the ablation or growth and delineate those changes to the surface and bottom of the ice, and do that over time so that we can evaluate what the drivers of this change are. Using the buoys, it's also possible to infer estimates of ocean heat flux or snow thermal conductivity based on how the temperature profile and the surface interfaces evolve over time. And here's what the type of data the SIMB can produce looks like. This is a buoy that we deployed with our partners at the Korean Polar Institute, KOPRI, in 2023. They put this out. It's one of those ones that just got stuck in luggage. It showed they went down in the hull of the ship, and all of a sudden there was a buoy there. They had to do something with it. So we appreciate them taking it out on the ice for us. It drifted from the Chukchi Sea north of Bering Strait, clear across the entire Arctic to near Greenland. So it monitored the growth and melt of the sea ice for 2 full years. The plot of the data from this first annual cycle is shown here. On the right, time is across the x-axis here at the bottom. In this case, from August 2023 through December 2024. The buoy tracks barometric pressure in the top pane. You don't see much of a seasonal cycle in that. And then air temperature in the second pane, where you can pretty quickly see the freezing temperatures arriving in October, deepening cold setting in through February, and finally warming back up to the brief summer melt in June, July, and August before freeze up begins all over again. In the third pane down, we see our depiction of the ice growth and ablation from the acoustic rangefinders determining where the surface of the snow or ice and the bottom of the snow or ice is, and allowing that to evolve over time. And then the temperature that's being monitored in the snow and ice is plotted as color, with the cool colors seen propagating down into the ice during the winter here, and then the ice warming back up throughout the column as solar heating in May and June warms it back up before melt initiates. We can also see in the bottom pane the water temperature, and we can see from this middle pane that we can pick out very important times in the course of the year, like when the bottom melt begins here, or when the surface melt begins, or when bottom melt ends. And I guess I have to admit at this point that Angela really shouldn't have invited us, because though we measure ice thickness, we don't really measure ice thickness. This is a measurement of ice thickness, but the important thing about the buoys is that they're really only in one place, and ice thickness varies a lot, even on a single ice flow, largely due to dynamics in the past. Instead, the ice mass balance buoys, we would argue, are much better at telling us about changes in thickness, not actually the thickness itself. So when we see people grab a single buoy measurement and say, well, ice is 1.2 meters thick in this region, we go, whoa, 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 hang on. We tried to put it in the typical ice of that region, but we're not sure. But during the Sheba campaign, they had hundreds of mass balance observations distributed across an ice flow, and there's a nice paper on that from points to poles that Jackie Richter Mengi is the lead author on. And in that, they showed that the changes in ice thickness tend to be much more uniform than the overall thickness. So while I won't say that this buoy, which showed while there was a 62 centimeter thick minimum for this ice in October, is necessarily indicative that 62 centimeters is the right thickness for ice in the area. This buoy does show that the ice in this region got thicker over the course of an annual cycle from 62 centimeters to 181 centimeters. That amount of growth is probably quite typical for the area. Same with the amount of melt here. This buoy is actually very highly unusual among the buoy record. It grew in net over a full annual cycle. If you go from here to August, it's 49 centimeters thick. It is the only buoy that we have had in the last decade that grows thicker over an annual cycle. Every other buoy either was crushed before it reached an annual cycle or showed thinning, which has been a very interesting part of the ice mass balance buoy record. Tends to be that if you start with mature ice, you don't continue to have mature ice. The buoys are also a shared polar infrastructure. First of all, the data of all the ice mass balance buoys we've deployed, now over 150 buoys. It's available to any researcher for any purpose at any time of the day or night. The raw data is available in real time on the Cryosphere Innovation website, and the clean data is archived with the Arctic Data Center or the National Center for Environmental Information, depending upon the NSF or NOAA funding source. The data sharing and hosting infrastructure, as well as the buoys themselves, are also available to any researcher. Cryosphere Innovations, the company, which is founded by one of our former graduate students, Cameron, sells the buoys for about 15K a piece. So you too could have buoys featured on the Cryosphere data website. And, act now while supplies last. Uh, but more seriously, we continue to improve and develop the buoys. Um, that's something Don will tell you more about how we're improving the buoys at the end. We really do depend greatly on partners willing to deploy the buoys and on a community that sees this as a resource and a long-term legacy of data collection so that people are willing to, while they're in the field for other purposes, put out buoys. And in recent years, we've also begun to see more and more buoys purchased and deployed under other programs. This is a great foundational observation of almost any time series campaign. And it's really important to realizing the potential of this tool that others are beginning to put them out. Ideally, when we've tried to think this through, we need about 40 or so of these things deployed each year to populate the full Arctic. Our best year so far has been 27, and we've got a lot of years where only 10 have gone out. So there's a need to continue to expand the network. The legacy of the buoys over the last 27 years has captured a major state change in the Arctic, though. In the Beaufort Sea in particular, the buoys have chronicled the state change from stable multi-year ice with limited melt prior to 2007 to significant meltout of thick multi-year ice that was transported into the southern Beaufort Sea during 2007 to 2020. That continuous graveyard cycle of big, thick, heavy ice going to the southern Beaufort and melting away to a present ice cover where multi-year and first-year ice in the southern Beaufort are of similar thickness, and they are kind of the thickness of first-year ice, and they tend to melt out completely in almost every year. And so, although the buoys don't take exactly the same trajectories from year to year, we can group the buoys into regions and look at the record for changes over long time, periods of time. And Don started this up a while ago by adding ship or field campaign based mass balance data from the 1950s through the 1990s, and that's shown over here. And then grouping the buoy observations into regions. So we have the Beaufort buoys, these green ones down here, and the buoys that are kind of in the intermediate latitudes, these blue ones up here, and the ones that were deployed up near the North Pole, the red ones there. Um, and what we see here is that in terms of the total amount of surface melt across the summer in each region, well, not that much has changed between the 1950s and now. There's a weak dependence on latitude. These Beaufort ones melt more on the surface than the ones up near the North Pole, but there's really no statistically significant trend, and this continues to the present. When we consider the bottom melt, well, quite a lot has changed actually, particularly in the Beaufort Sea, where the pre-2000 field campaigns measured 5 to 15 centimeters of bottom melt. Over a meter of bottom melt has occurred commonly starting in 2007. In the intermediate latitudes, we have less early observations, but there's some indication that we've had an increase in bottom melt. And at the higher latitudes, we don't have anything from far back to compare to, and there we don't really have an ability to say whether it's changing or not. There's some evidence in the short-term record that there's been an increase, but that as we continue to extend this record, there's enough noise. It's hard to make a trend out of it. What is clear is that the bottom melt is what has contributed to the strong loss of multi-year ice and poor survival of the first-year ice in the Beaufort. Elsewhere, we can just say that the variation in melt is high, and the trends, if they're present, are small compared to this variability. Larger buoy arrays might help us understand what fraction of this variation is spatial rather than interannual and help us improve our ability to resolve more subtle changes. So in 2024, we deployed some buoy arrays, 8 buoys in the Beaufort Sea, to target this intra-regional variability. We put the buoys out by aircraft in March, and a representative plot of one of the buoys is over here at the right. The 8 sites behave broadly the same. There's no annual cycle. In all the sites, the ice melts from about 2/3 from the bottom and about 1/3 from the top until it all disappears in late July or early August. And that's with about 5 weeks left in the melt season. It didn't just barely melt, it melted with authority. And all 8 buoys did this. The ice we started with is quite different than in earlier campaigns. So at the latitudes of the northern buoys of this array, C and I here in the picture, our buoys deployed in this area in pre-2016 and field observations from the same area had an average maximum ice thickness of 2.75 meters, 2.76 meters, with 35 centimeters of snow on top. Classic old multi-year ice. Here in 2024, we found an average ice thickness of just 1.18 meters and an average snow depth of 0.11 meters. And we were looking for the thick stuff, I promise you. We wanted to land on the thickest stuff we could find. So it's just an entirely different ice regime. The ice was the thinnest average we've put our buoys in the Beaufort so far, beating 2023 and continuing a downward trend in the ice thickness we're finding. The ice was both multi-year and first year, but unlike years past where the thick multi-year was often advected into the southern Beaufort Sea, the multi-year sites had basically the same ice thickness as the first year ice. They just had twice as much snow on them that prevented the growth a little bit. There was also a change in the melt onset regime. Bottom melt, which kicks off right about here, uh, started about May 19th on average across the buoys. This is almost 10 days earlier than any prior year. And meanwhile, snowmelt onset averaged June 8th, which is really near the long-term average, actually. The low overall ice thickness, slow growth rates in the winter, and early bottom melt onset together appear to be indicative of an increase in ocean heat flux through the winter. This was repeated for the 2 buoys we deployed in 2015, and again, where bottom melt began 2 to 3 weeks prior to surface melt, overall winter growth was low compared to previous years, and bottom melt onset appeared to occur in a way that was indicative of a greater ocean heat flux. So from these ablation rates, we can calculate the amount of energy used in ice melt, and that's plotted down here at the bottom right. We find that the overall energy used in melt is lower than in some prior years, but that's a trick. It's only because the ice was so thin, there wasn't the possibility to use more energy. The rate of melt energy usage was the highest we have observed, with 181 megajoules per meter squared on average by July 1st, which is more than double the pre-2016 average. Variation between the sites was about 50% of the mean, which is to say the variation between the sites in this region is similar to the variation we've previously seen between years. In 2024, we also deployed a 9 buoy array in the Lincoln Sea, north of Greenland, for the NASA Arc-6 campaign. The buoys were modified buoys, specially modified to be deployed in very thick ice that we expected to find in this region. We removed the lower temperature strings, which is why there's no temperature shading in this region of the plot right here, to save cost. So here in the last refuge of the ice of the Arctic, we were prepared for deployment in ice of up to 5 meters thick, and we expected to find 4-meter thick ice to be common. The thickest undeformed ice we found, though, during our deployment landings was only 2.8 meters thick, and our deployment average was 2.15 meters thick. This is really notably thin compared to prior expeditions in the region, which found modal ice thicknesses near 4 meters across the Lincoln Sea. Still, surface and bottom melt, they were in line with the long-term average for other high Arctic mass balance observations at 39 centimeters average from the surface and 21 centimeters from the bottom. Total melt varied only about 25% about the mean, and that's about half the variation we see between buoys of different years in this type part of the Arctic. So these levels of surface and bottom melt, they're not enough to account for an apparent thinning of the ice in the region from 4 to 2 meters. Unfortunately, we didn't have any buoys remain in the region. They all drifted out or died to see whether winter growth has also changed. So that would be a great target for future buoy deployments. This is a hard region to keep buoys in because it's a divergent zone. Everything drifts out of this region. Also, over the course of 2023 and 2024, we had 8 buoys deployed in the transpolar drift. These averaged 1.78 meters in thickness with an average of 45 centimeters of snow. That's more snow and less ice than the long-term average in this area. None melted out completely. All but one ended the annual cycle thinner than they began it, and that's the one that I talked about before, where we did have one buoy get thicker. Surface melt averaged 28 centimeters, bottom melt 37 centimeters, and these were also pretty typical values. So putting those newer values, 2024 values, onto the old plot here, we can see that the surface melt in the Beaufort Sea is right in line with the long-term average. And the high Arctic sites, same. Any change in the surface melt is small relative to the interannual variability. The change in bottom melt, well, that's reinforced. Only now we have to put an asterisk on top of this column here because the ice melted out completely with 5 to 6 weeks of melt season remaining. So the potential bottom melt is actually greater than what is reflected here on the chart. In the higher Arctic regions, not much has changed. And so the bottom melt remains the driver of the changes. And it leads to kind of an interesting possible theory about the nature of the mass balance changes in the Arctic. The ice we've been deploying the buoys in has unmistakably thinned in all regions of the Arctic. And that's consistent with all the other records of ice thickness. But we've only detected a change in the melt behavior in the Beaufort. So what's causing the thinning? Well, perhaps most of the loss of the ice mass is indeed occurring due to changes in the melt rates only at the periphery of the basin. Or perhaps the ice mass in these balance in these regions is being reduced by a lack of growth rather than an increase in melt. Those are actually the questions we're trying to answer over the next few months as our buoy project's kind of nearing its end, at least its current form. We're taking a fresh look through the whole buoy archive and seeing if we can learn a little bit more about the trends in growth now that we've got another 5 years worth of data. We're also fielding a whole bunch of new sensors on the buoys, and for that, I'll go ahead and turn it over to Don.
Okay, so from the very beginning, the seasonal ice mass balance buoy has been designed with an open architecture to make it easy to add sensors to it. And we've been doing that in two ways. One, we've just been adding sensors directly to the buoy, sensors like radiometers or conductivity cells. And two, we've also been trying to explore spatial variability. With the seasonal ice mass balance buoy, as Chris alluded to, it raises a philosophical question. What good is a point measurement? And it turns out the answer to that is it depends on what parameter you're talking about. For some parameters, a point measurement is great. For others, it's just okay. And for some, it's like, no, we want more than that. And we've been looking at that in terms of things like ice thickness and snow depth. So just to give an example of what we've been doing, could I have the next slide? One of the things we've done is add broadband radiometers to it. This was a project, a senior thesis done by Mary Tobin, and you can see in the picture in the upper left, there's 3 radiometers. One is on top of the buoy, looking upward, getting the incident sunlight. Another is off to the side of the buoy, looking downward, getting the reflected light. And the third we can't see because it's underwater. And from those 3 sensors, we can use that data to do a complete partitioning of the incident solar radiation. We can take the incident and reflected, combine them, and get the albedo, which you see in the plot on the left, for a little over 2 weeks. And we see during that time for snow-covered ice, the albedo was around 0.8 something. We can also take the incoming sunlight, compare it to what's transmitted through the ice, and get the transmittance. And that's on the far right. And let me note that it has a completely different scale. And we can see from that that during this time, we were transmitting less than 0.5% of the incident sunlight. You combine these two and you can back out what the absorptance is, what fraction is absorbed in the snow and the ice. And we see for this particular case, it was a little under 20%. We could easily apply other sorts of optical sensors to look at spectral measurements or observations of photosynthetically available radiation. So this is just one example of sensors we can directly add to it. Next slide, please. Another thing we can do is look at spatial variability. And snow is something we really wanted to look at the spatial variability of. And that led to a graduate student, Ian Raphael, is creating the Snow Thickness and Temperature Observing System, SNOTATOS. It's a way to explore the spatial variability of snow depth. You can see there's a central node, in this case of a SIMB, and it's surrounded by nodes that just measure snow depth. Has the same acoustic sensor that the buoy has. It also has a data logger, a battery, and a transmitter, and it transmits the data back to the central controller, in this case an SIMB, that aggregates the data and sends it back home via Iridium. You can see on the right, the top picture there shows one of these nodes being installed. And the picture beneath it shows an array. It's a little bit hard to pick them out, but wherever there's an arrow, there was a SNOTATOS node there. And the key thing is we can put these out wherever we want over hundreds of meters. The only limitation is it transmits via radio, so you need direct sight with the central controller. This particular installation was, we didn't even need an SIMB for it. It had its own standalone controller. Next slide, please. Here we see some results from a deployment using 10 nodes from late April through the following January. And you can see just from the beginning, looking at the start, there's a lot of variability in snow depth. If we look at the trend from May into early June, the snow depth is steadily increasing everywhere we look. And then it's steadily decreasing. The snow melts. When the snow is completely gone, varies from around June 10th to July 5th. So we see that difference in snow cover definitely has an impact. And then once the snow is gone, the ice melts until finally in early August, freeze up begins and we get the next covering of snow. So from SNOTATOS, we can look at what's happening at individual locations, or we can combine it all and look at the statistics. And that's what's shown in the whisker plot on the right-hand side. We see a time series that aggregates the data from all the 10 nodes to calculate the mean of those, the median, and the standard deviation, and the full range. And so these are just a couple examples of how we can augment the seasonal ice mass balance buoy, but the important thing is the request line is open. We're looking at other ways to expand this. So if you have a favorite measurement that you think would be really useful to add to an SIB, please contact us. Would be delighted to talk to you about it. Thank you.
All right. Thank you, Don and Chris. Maybe we have time for one quick question before we transition over to our next set of speakers. So I have one. Chris, you mentioned that kind of as an ideal, having about 40 buoys deployed every year would get you good coverage in the Arctic. Is there a kind of ideal set of deploying networks like with the SNOTATOS or with several buoys deployed like for Arc 6? What's the strategy for deploying that
Yeah,
amount
it's,
of?
it's a good question. It has kind of probably a longer answer than right now. But like, what we really are still learning that I think when I put out the array in the Beaufort in 2024, I showed the one buoy. They all look like that. It really didn't feel like I looked at them at the end and was like, wow, I should have put those buoys in other places, but we actually didn't know that they were all going to be that similar until we, ran the test. Whereas in the Lincoln Sea, they were quite different from one another, quite different thicknesses, quite different evolutions, quite different timings of melt. And so I think the answer to that is probably actually regionally dependent. In a place like the Lincoln Sea, where, well, you could go out Fram Strait or you could go for another lap around the Beaufort Sea by being 40 miles apart, well, you might actually need rather a dense network to capture the range of possibilities. Whereas in the southern Beaufort, where you're all going to melt out and the ice is all about the same thickness now, which it wasn't in the past. It may be a little bit more of an answer of, well, we just do it. We can just put a couple out and capture that. The snow measurements, we've done a lot of work, and Ian has a paper coming out on how many measurements do you need to put out on an ice floe to get within n centimeters, where n is 2 or 3 centimeters of the mean snow depth. And the answer is about 10. So we do have a little bit clearer answer for that, where one of these node networks needs to have about 10 members, so that you can remove that local scale spatial variability and get an idea of kind of the average snow depth rather than just which dune you happened to measure it in.
Yeah, great. Thank you. Feel free to add additional questions you may have for Chris and Dawn to the chat. We can come back to those at the end. But now I'd like to welcome our next speakers. Um, this talk will be given by Jesse Wimert and Nathan Kurtz from NASA Goddard Space Flight Center, where Nathan is chief of the Cryospheric Sciences Laboratory and also deputy project scientist for ISAT-2. So today, Jesse and Nathan will be talking about release 7 of the ISAT-2 Sea Ice Freeboard product.
Hello, everyone. Let me get window sharing. Can you all hear me and see my screen?
Yes.
Great. Okay, so thank you for the introduction. Thank you all for having us today. My name is Jesse.
Can you go to presenter mode?
Can you not see it?
You're still in like the PowerPoint screen.
Hey, is that better?
Looks the same.
Is that better?
Perfect. Good
Okay.
now.
Sorry about that. Okay, so my name is Jesse. I'm the developer for the Sea Ice products for the ISAT-2 mission. I'll be presenting with Nathan, deputy project scientist. So ISAT-2 we don't produce a thickness product, but we do have a freeboard product. So we'll be discussing here today. And as Angela mentioned, this past year we released version 7. So this will be the updates we've created. Just as a quick background for ISAT-2, we have 4 sea ice data products. ATL7 is our surface heights. ATL10 does freeboard heights, as well as leads and reference surfaces. And then we have 2 graded products, ATL20 and 21. So just an overview, some of the big updates for this release 7 was a change to some geophysical corrections. We updated an auxiliary file, the sea ice concentration daily file. We implemented a DDA bifurcation algorithm, which allows us to flag potential melt ponds. And then we added a alternate distribution model, log normal model, for waveforms that don't provide a smooth Gaussian return. So first is a look at the change in geophysical corrections. Release 6 and earlier of our code using an inverted barometer correction, which we computed within the code using the available metadata. For release 7, we decided to change to the dynamic atmosphere correction. This is derived from a CNES dynamic atmosphere product, and this was already available in ATL3, so it was very easy to implement for us. This is a more localized dynamic model. It takes wind into account, as well as the pressure changes that our previous model did. And very importantly, this brings us in better agreement with other ISAT-2 data products, such as the Oceans products or ATL12. These plots show a monthly average comparing our previous inverted barometer versus DAC geophysical correction. And as you can see, most of the areas is only a small change and it's pretty flat. But near the shoreline of Russia, we see some bigger changes. Bottom is one granule, one overflight that shows these differences. As you can see, the dark red is the deck. And there's much more variability near the shore compared to the previous inverted barometer correction. But as we get closer to the pole and away from the shore, there's a small change in value, but they follow similar trends. We changed the daily sea ice concentration file, whole bunch of reasons to make that change, but just the background is we use these sea ice concentration files as a filter. We use it for ATL7 if there's a 15% or greater sea ice concentration value, we go ahead and make our measurements, but we filter out anything outside of that. That's to prevent too much open water and noisy data from getting in. And then we use a 50% cutoff for when we compute leads and reference surfaces on the ATL10 freeboard product. We were previously using the AMSR2 sea ice concentration file from JAXA. It was a finer resolution. We thought there was more change in a better model, but we got told that it was going to be retired on September 2025. Because of this, we made the change to SSMI. We chose this so that we would have a consistent model throughout the mission when we reprocess the ATL7 data. So from launch to present, we're using the same SSMI data. However, January of this year, just a couple weeks ago, the SSMI data ended, and the NSIDC is now going to be creating a new data product using JAXA AMSR2 data. So still using SSMI, same data file, but starting this month, we are changing some of the inputs from it. The plot on the right just shows a monthly average of sea ice concentration files. On the left is AMSR2, and on the right is SSMI. You can see on the bottom of Antarctica, there's slightly lower concentrations for SSMI compared to AMSR2. We're not expecting too many changes from this, but there will be some changes, possibly some lost granules from this change. We also introduced the DDA bifurcation algorithm. This was developed by Ute Hersfeld in Colorado. We added this to the ATL7, so this provides an alternate surface find algorithm in addition to the ATL7 one already there. So this produces surface heights along the entire granule, but it also allows for bifurcation. So if there's a potential melt pond, it will produce a top surface and a bottom surface height. You can see this in the long track plot on the bottom. This green line maps out what the DDA found as the bottom of a melt pond. Green and red are the ATL7 heights, and what the red indicates is we flag these ATL7 heights because they might be potential melt ponds, might be contaminated. So right now, all this data is flagged, but nothing's being done with it by default. But there is a flag option for when we compute freeboards to throw these to ignore these heights. So we started looking into some of this, but there's more analysis to do. But this could have an effect on leads and reference surfaces. The one knows that there's filters and different thresholds to pass to mark this as a potential melt pond. So we're not looking at little melt ponds because they could be falsely flagged. So we're only looking at large melt ponds right now. Next, I'll pass it over to Nathan to discuss the log normal introduction we did.
All right, thanks, Jesse. Yeah, the other major change that we made has to do with how we're fitting some of the waveforms. What we had found is that when the surface is very rough, the fit was being flagged as poor frequently. And I mean, this happens over ridges. And so what was happening in the older versions is we were just losing that data. Because if the fit was flagged as being too poor, then yeah, we were just throwing it away. But what we decided to do for release 7 is, instead of assuming that the surface height distribution is Gaussian, we looked into, what if we explored an alternative distribution? So we looked at log normal, which had been analyzed from airborne data in the past. Log normal can be a better representation of the surface height distribution. And so introducing this on the plot on the right here shows the difference between a Gaussian and a log normal. So the more rough the surface is, the more skewed the tail is in the log normal, whereas a Gaussian is symmetric. And in that middle panel on the bottom is the histogram of the photon heights, and the Gaussian is in the darker color, and you can see it's trying to fit a symmetric distribution to something that's not symmetric, whereas the log normal is trying to fit, again, a skewed tail to that. And so what we found is that the log normal does a lot better job in some of these rough and ridged areas. And that plot on the bottom is, showing a imagery in where it's flagged in red as where we would have lost data otherwise in the old releases, and now we're able to recover that with the log normal heights. So we're still only reporting data that are flagged as good with the log normal, but I think we're recovering, I forgot the exact percentage. It might be something like 80% of the bad fits that were thrown out before. So we're recovering a lot more of these heights that were thrown out before, and now they're flagged as good fits. And so that is raising the mean freeboard that ISAT2 is reporting, because now we're better sampling the ridged heights. So next slide. And this is the last slide. Or, I think this is the second last slide. The map on the left is showing the height difference between release 7 and release 6. And so where it's the darker blue, you can see that we're reporting a higher height. And so what you really see there is that, in these, where it tends to be more ridged and rough, that we're getting higher heights, because again, we're actually recovering those heights that we were throwing out before. We did a comparison to Operation Icebridge underflights of ISAT2 in 2019. And we were comparing the distribution of the height distributions that we found from the airborne data with a much higher resolution LiDAR compared to ISAT2. And you can see in the bottom plots, in especially in the semi-log plots, where the OIB is in the blue, so showing, again, kind of a skewed height distribution from ridges. The old ATL07 data wasn't capturing those, whereas with the log normal, we're much better able to capture those. And you can see that in the full histograms, not necessarily the log norm or the semi-log plots. So yeah, we're recovering a lot more data than we had previously. And so yeah, I think next is the last slide. And so this is the mean result over the full cycle of ISAT2 since launch. So this is just mean Arctic and mean Antarctic freeboard for release 6 and release 7 over the full cycles. These are monthly averages. So the blue is the new release 7. And so you can see that, it generally tracks for the Arctic, but, towards the peak of the growth season, we are getting slightly higher freeboards. So the mean freeboards are somewhere around 0.1 to 1.4 centimeters higher overall. Translate that into thickness, it is significant. It can be up to about 10 centimeters or so on average. So, and again, this is just recovering what we were throwing away before. It's quite a bit different in the Antarctic below, and it's just the Antarctic has such a different cycle, seasonal cycle, and so there we're seeing even slight lowering of the freeboard of negative 0.1 centimeter, and then at the peak of the cycle, we're seeing average freeboards up to about 4 centimeters higher. But again, I think that's a lot due to the fact that what's left in the Antarctic, at the peak of the melt season, is more just that really ridged ice. And so that's what we're picking up. But again, some of the changes in here have to do with ice concentration or the geophysical corrections, as Jesse mentioned as well. So it's a kind of a conglomeration of everything. I think a lot of this is the log normal though. So that's primarily what we're seeing. But now that we have all the data processed, we're doing an analysis and, trying to quantify all this and write this all up. But yeah, this is the difference in what we're seeing in the products and what's out in the data moving forward. So yeah, happy to take questions.
Thank you, Jesse and Nathan. Yeah, so let's open it up to questions. Morteza, you have your hand raised?
Yes. Thank you, Nathan and Jesse. Sorry that I brought this question to this particular meeting. Great explanation. Now I'm understanding a little better as for what to expect about rougher ice. I did also want to ask a question about the energy levels that changed. When was that, and was that to kind of compensate for the aging sensor, and how do you suspect, if at all, that would affect the measurements?
Yeah, that's a great question. So I think we raised the energy level, I think it was October of 2025. And that's exactly it. We raised the energy level to compensate for the aging sensor. It's a combination of the laser transmit energy is going down as it ages, as well as the receiver sensitivity is going down. So we monitor what we're getting back in terms of the photon rates. We're trying to maintain kind of a photon rate that's fairly constant across the mission. And so yeah, this is the second time we've raised the energy level, and again, kind of bumping us back up to where we were before. Then the question is, well, how does this affect the measurements? This is something that Jesse and I are working on for release 8, is that there's two impacts. There's the standard product right now aggregates 150 signal photons to produce the measurement, and then from that we get the length of the segment that we aggregated over. So when you're losing energy, you're going to have to aggregate over a longer segment to get those signal photons. So that's kind of one. The other is that we have thresholds on how we determine leads. So we use specular returns from very flat surfaces as leads. And that threshold is not dynamic. It's static. And so what happens then is when the energy level is changing and that threshold is static, you're probably going to be flagging less leads. We've also found that, this is going to depend on your angle of incidence. So there's a lot of things that they're going through this. And so one of the things that we're working on right now is, can we change the static thresholds into something dynamic so we can more accurately flag the leads, which maybe you're more interested in, Morteza. But yeah, this is really ongoing for release 8.
Amazing. Thank you for the explanation. Yeah, we did some machine learning on lead detection, and particularly trying to exclude background rate, just to see if we can do that sort of consistently during the polar night, and the background rate wasn't as useful, and results are interesting. Unfortunately, that was a side project, but this motivates me to bring it back up and activate it, and happy to send to you whatever we find.
Oh yeah, thank you. That'd be good.
Nguyen?
Yes. Hi, Nathan and Jess. Thank you so much for that. And so you were talking about the release 6 and 7. I was wondering, are those data kind of available to the community? If so, could you please share the link with us?
Yeah, those are all on NSIDC. I can send a link, and it's just make sure you're collecting the right version. I can put the link in the...
Right. Okay. And also your data looks like you, especially the last one, Nathan, showed the time series. Is that you said is average over the Arctic? So it's kind of like a aerial mean, right?
Yeah, that's right.
Okay, thank you.
And maybe to add on to that, we do have two different products for sea ice freeboard, and those are at NSIDC. So ATL-10 are the along track, like they're the segments that we get along the satellite track. But then ATL-20 is their monthly mean or their monthly aggregates. So we put those at a 25 kilometer resolution. So it's, more comparable to like the passive microwave data.
Beautiful. Thank you. That's good to hear. Thank you.
Okay, additional questions? Okay, I do see a question in the chat for Dawn from Bjorn Erlingson. Have you converted the ice growth rates in terms of latent heat flux in watts per meter square? If so, what order of magnitude did you get?
I was just starting to type an answer, and answer is it varies a fair amount depending on the growth rate, but it's say very roughly on the order of like 10 watts per meter squared, maybe as much as, well, and that's for just standard ice that's not really thin or anything. Say 10 to 20.
Thanks, Dawn. And Jesse added the links to ATL-07 and ATL-10, so those two separate data sets in the chat. Yeah, I'd like to welcome any more questions. If not, I'd like to thank our speakers again today for giving us a couple of great presentations. Thank you both, Dawn and Chris, and also Jesse and Nathan. This is really informative, and we're really grateful for you all for taking the time to present for the CS community on IRPIC. All right, thank you all.